For more information, please visit SGMAK Associates website.
This model is an example of a Monte Carlo simulation used to estimate the value of constant pi. Pi is defined as the half of the ratio of circumference of a circle to its radius. This is an example of Monte Carlo simulation since, unlike a dynamic model, passage of time plays no role in the model. Each entity represents a trial to select randomly a point inside a square of side R. The x-coordinate and the y-coordinate of the point are selected randomly. The origin is set at the lower left corner of the square. Following selection of a point, a check is made whether the point is inside or on the quadrant of a circle of radius r that has been inscribed in the square. A counter is incremented if the point lies inside or on the circle, and then the entity is disposed. A batch size is specified in the simulation model. Batch size decides how many entities are to be tried to be used in that particular simulation run. The last entity of the batch is used to estimate the value of pi by using the following relation. Pi is given by 4 times of the ratio of number of points inside or on the circle divided by total number of points tried, or equal to 4 times the number of points inside or on the circle divided by the batch size. A larger batch size is expected to provide more accurate estimation of pi. Once again, this is a very simple example, shows a sampling experiment, and a Monte Carlo example, also known as a static simulation, because we are not interested in any dynamic behavior of the system. We have a simple task of selecting randomly a certain number of points and checking whether each point is within a circle or not, and estimating based on the outcome. So once again, Monte Carlo simulation model, also known as static simulation model. Later on, we'll describe other interesting Monte Carlo simulation models.
Pi value estimation. This is an example of a Monte Carlo simulation or a static simulation. Unlike a dynamic simulation where we study the behavior of a system as it changes over time, time plays no role in a static simulation. In this example, we randomly select 10 points on a square that inscribes the quadrant of a circle and count the number of points on or inside the circle. We use this information to estimate the value of P as described next. There is no dynamic behavior that is of interest to us. Problem statement: use the following sampling experiment to estimate the value of P. Draw a square beside the units. Inscribe a quadrant of a circle of radius a. Set the origin of the coordinate system at bottom left corner of the square. Generate 10 points randomly within the square and count the number of points that fall on or inside the circle. The estimate for P is given by the expression P equals for asterisk number sign of points on or inside the circle /n. Develop an arena model and solve the problem. P-value estimation: the area of a circle is P*r circumflex accent 2. To estimate the value of P, consider the quarter of the circle in the first quadrant, the area prescribed by P*r circumflex accent 2/4. See figure. The square in which the quarter circle is inscribed has an area of r circumflex accent 2. Consequently, P equals 4 times the ratio of the area of the quarter circle to the area of the square. A Monte Carlo simulation can be used to estimate this ratio and therefore the value of P. The ratio can be estimated by randomly choosing points x, y within the square and keeping track of the number of points that fall within the quarter circle. Those points were x circumflex accent 2 plus y circumflex accent 2 less than equals r circumflex accent 2 versus the total number of points tried. We may assume that the proportion of number points falling on or inside the circle is proportional to the ratio of the area of the quadrant to the area of the square. The constant P can be estimated by multiplying the ratio by 4. The accuracy of the estimate of P is dependent on the number of points used. The arena model is shown next. This is an example of Monte Carlo simulation model. A brief description of each module is provided next. The entity represents a randomly selected point on the square. Create. The first entity arrives at time t equals 0 and thereafter after a regular interval of one time unit in minute selected arbitrarily. The time between arrivals has no physical meaning in this problem and is used only to space the arrival of entities to the system. Maximum number of entities that can arrive to the system is set arbitrarily equals 1500. Each entity is an agent that represents a randomly selected point on the square and updates all system variables as it flows through the model. Assign. Use a circle of radius 6 units. Select the point randomly within the square by assigning the x-coordinate. Data lu equals 6 asterisk uniform 0 1 and the y-coordinate. Eval u equals 6 asterisk uniform 0 1. The uniform A, B distribution returns a value between A and B without any bias. Data lu equals 6 asterisk uniform 0 1 selects a point randomly on the side of the square aligned with the x-axis. The ALU and the evalu are system variables associated with each sample point. These could have been defined as attributes as well. Update the state variable. Number count. Number count represents the total number of points already sampled. Decide module is used to check whether the point selected randomly is inside or on the circle or outside the circle. If true, update the state variable number in by incrementing it by 1. Otherwise, dispose the entity. Assign. Update the system variable number in by adding 1 to the current value. The state variable number in represents total number of points counted thus far that is inside or on the quadrant of the circle. Decide. Check if the current value of the variable number count is greater than equals 1500 or not. This condition will be true when the value of the variable number count reaches 1500 for the first time. If true, estimate the value of P. Otherwise, dispose the entity. The following assign module estimates the value of P assigned. Estimate the value of PP equals for asterisk number in slash number count. Value of P is assigned to the variable pi underscore estimate. For this replication the value of P equals for asterisk 1178 over 1500 equals 3.1413. 1178 points out of 1500 selected randomly within the square are within or on the circle. Record The current value pi underscore estimate is assigned to the tally variable approximate underscore pi underscore value. The entity is disposed. This exercise of estimating the value of P is an example of Monte Carlo simulation. Accuracy of the estimate can be improved by using a larger value of n results for P with n equals 1500, 5000 and 10,000. Then value of page 1500 p equals for asterisk 1178 over 1500 equals 3.14135000 p equals for asterisk 3941 over 5000 equals 3.1528 10000 p equals for asterisk 7820 over 10,000 equals 3.1280. The students should pay attention to understand why this model is called a static model and not a dynamic model. Table: the salient features of estimation of P model. Type of model: stochastic, static model or a Monte Carlo model. Entity definition: entity has no physical meaning. Entity is an agent that draws random variables from a/b distribution and performs some bookkeeping tasks. Resources: use none. Arena: features used assign and decide modules. Run length determination based on number of replications. Output analysis: treat it as a terminating system. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.